Welcome to the recording of section 3b. Recall that in section 3a, we talked about linear maps, and sometimes we say it's like linear transformations from a vector space V to another vector space W, or V and W could be different or could be the same. And then so in this section 3b, we're trying to consider if there is a linear map from the V to W, and what are the elements such that in the V, such that the T of those elements applied on V equal to 0. And if we collect all those special elements of vectors in V together, we give it a name, call it a null space. Right, that's basically all the elements in V such that the T of V equal to 0. And so that's one thing we're interested. And the other thing is we consider what happens if you let the input run through the entire vector space V, and you collect all outputs. Of course, each one is in the vector space W there. But sometimes maybe this all this collection, the set of all the collection of all inputs will be equal to W, sometimes may not, right? So then the collection of all those outputs is called the range. And then we want to understand what is some property of the range. For instance, that is a subspace of W, right? And then if the range is equal to W versus the case the range is not equal to W, then that's going to be, we want to separate these two cases. So the first subspace, the null space of T, that is something to connect with a concept. We say the V is injective, or this linear map is injection, and then whether the range is equal to W or not, that has something to do with whether the T is something we call surjective or is a surjection or not. And so then after we define this, then we're going to look at, well, can we say something about the dimensions of those vector spaces or those subspaces? Is there any connection there? All right, so that's the whole picture of what we're going to do in the section 3b here. And this is another long section cover the different definitions, examples, or properties, proofs. So we're probably going to do like at least 2 or maybe 3 recordings. All right, so let's see how it goes. So let's go ahead, start looking at the first definition. Let me share the screen here. Okay, good. Vector spaces, null spaces, and ranges. All right, so let's define for NAT. All right, this is from LVW. Remember, the LVW, this itself is equipped with the addition and the scalar multiplication, or between the linear maps, or this is a vector space, and any element there is a linear map from the vector space V to the vector space W. Right. Then for NAT here, the null space of T, right, and we use this notation NULL and then write the T after that, or it's a commonly used notation. This is the subset of V containing of those vectors that T maps to 0. All right, we'll give a more mathematical notation in the next line there. But keep in mind, all right, so we have a V there, we have a W there. All right, so when we're talking about at least right now a subset of something, then you want to make it very clear, right? So which is which, right? So is this a null space? Is this a subset of V, or is this a subset of W? Or it's clearly this says it's consisting of those vectors in V, or is a subset of V, or such that the T of V equal to 0. That 0 is the 0 vector in the vector space W. All right, so your V can be 0 cannot be 0 depending on each circumstance, right? Of course, the 0 element in a linear map in the V is always included in the null space because we know T of 0 is always equal to 0 when T is linear. But then this 0 in our definition here means the 0 in the vector space W. All right. So then let's write a set notation for this. So the null T is the V. All right, so this lowercase v in the vector space V such that the T of V is equal to 0. All right, equal to 0. So let's go over some examples here. We're going to cover some of the book mentioned. We're going to cover some part of the book not mentioned. Use the linear algebra. So let's make the first one is let's consider a T from R2 to R2. Such that the T is defined as this. So if there is the ordered pair xy, then T will just switch the x and the y positions. All right. So if, for instance, if your input is 2, 5, then the output is 5, 2. If your input is -1, -3, the output is -3, -1. All right. So that's how this map works, and it's not very hard to check this is indeed linear. So check the T of xy plus maybe uv is equal to T of xy plus T of uv, and then check the T of NA like lambda times xy is equal to lambda times the T of xy, or you can verify this is linear. So then let's consider what is the null T here. So the way to think about this is you ask yourself, if I send in an xy, I want, no matter what xy is, I want the output to be a 0 vector in R2. So that means the output is 0, 0, right? But how do you get that output? Well, that is obtained by switching those two numbers. So if you switch these two numbers back, that will be our input. Well, then when you switch 0, 0, you still get 0, 0. So then this one, the only element belonging to the null space is 0, 0. Because if there's a vector which is not 0, then that means there at least one element is not, one coordinate is in that ordered pair is not 0. So that coordinate will be either x or the y, doesn't matter, but then when you finish, that coordinate still remain either in the y or x position in the resulting vector. So then the resulting vector is not 0. All right, so the only thing here is a 0 vector. And then, so this tells us, yes, the smallest one we can get is 0, 0. And like this case, we do have a null space, which is non-empty, is containing at least a 0 vector. And let's look at another one using still some of our linear algebra knowledge here. So let's consider the T is this one, is a T of xy equals x plus 2y, and then 2x plus 4y. All right. So then again, input is NA vector in R2 with 2 coordinates. The output is NA vector in R2 with 2 coordinates. All right. And we use this kind of linear combination between x and y to make the 2 coordinates in the output vector. You can check this again, it's linear. Then if you want to look for the null space, we have to do the same thing, but this one we're going to write it down is, well, the null space means you look for the xy such that the output x plus 2y is equal to 0, and then 2x plus 4y is also equal to 0. However, these two equations, if you look at them carefully, then obviously the second one is just the first one multiplied by 2 on every term. So they are not independent equations, right? We know if there are 2 variables, 2 equations, then you have a chance to get a unique solution. But this one, actually, there are 2 variables, only 1 equation, and that's a homogeneous equation, 0 on one side. So there are infinitely many solutions in this case. So we cannot actually find a single ordered pair or just a few ordered pairs such that the T applied on this equal to 0, and that's all of them. No, that's not the case. So in this case, the null T is just all this xy where the xy satisfy one of these two equations, we're just going to take the first one. All right, so x plus 2y equal to 0. Right? For instance, if x is 2, y is -1. Well, that's going to work. You can check that. If x is 6, y is -3. That's also going to work. And if x is 0, y is 0, of course, that's also going to work. So there are infinitely many vectors in this null space. And we're not saying this is equal to R2. That's not the case, because this is a straight line, right? Geometrically, this is a straight line R2. Any point on that line will be will belong to this null space of this linear map. All right, so that's what we're saying. And now let's use something not just the vectors in R2. All right, so let's start thinking some other linear maps we introduced in the section 3A, right? So for instance, the book used this example saying, recall that, all right, so we defined this differentiation operator, or T, is from, take a polynomial, this will be P of R, or it's a collection of all the polynomials to the same vector space, the P of R. And the way they generate this is any polynomial P, when you apply the operator T there, it just differentiates this function once. All right. So this one, so what is the null space of this differentiation operator? Right. So you input something and then you differentiate that. You want that in order to make this P to be included in the null space, you want the derivative equal to 0. Right? So then this is something, we're already learning in the calculus 1 class is what kind of functions. There's a family of functions whose derivative is always equal to 0, and only those type of functions, the derivative is equal to 0. All right, so that is the corollary by the mean value theorem. So then we know that is the constant function, right? 5 square root of 2 pi or 1 over 3, right? Whatever. So those constant functions, the derivative is always equal to 0. So this null space here is equal to the set of all constant functions. All right. So this is another example showing us how we can determine the null space. And of course, all constant functions, this is not the entire polynomial vector space, right? We have a linear function not there, quadratic function not there, or many other polynomials not there. So this is a proper subspace of the P of R, all right, this null T. And one more, right, using the polynomial. So we still consider T are from the L P of R to the P of R here. Right? And then we define the T of P of X. This is multiplied by X squared, right? So in other words, any polynomial, you just multiply X squared in front of the entire polynomial, and then you increase the degree by the degree 2 here. All right, so this is the another example we introduced in the section 3.1. We left, I think, as exercise, let everyone to verify this is indeed a linear map. All right, for that. So then, what is the null T for such a linear map? Right. So then this one, you want to have something when you multiply by X squared, that Px times X squared is equal to 0, right? Only when this happens, that polynomial P is in the null space of this T. But if you have X squared times P of X, which is equal to 0, then it's clearly, if you have a non-zero polynomial times X squared, you're not going to be able to get a 0. All right, so the only thing which is going to work in this case is your P of X is a 0 polynomial, then times X squared is still a 0 polynomial. So in this case, we're going to see this null T is equal to 0. All right, and remember this is not, so this is like the 0 polynomial. In other words, this is like a constant function. No matter what X you use, the output is always equal to 0. All right, so then that is the second case. And then the last example here using something I think we call kind of backward shifting, right? So you kind of shift the all the coordinates to the left-hand side by 1 unit. All right, so x2 become x1, x3 become x2. That's something we talked before. All right, let me write down the definition here. So this is from f infinity to f infinity. All right, this is a kind of infinite vector. All right. So because 1, we begin from like x1, but then we never terminate at any position. I just keep going on forever. So then this t of x1, x2, x3, and so on. So then this t shift this to x2, x3, and so on. Right. For instance, if you begin with something like a 1, 2, 3, 4, keep going forever, then the resulting vector will be 2, 3, 4, and then keep going forever. Right. So this one, you ask yourself, if I have this t of x1, x2, x3, this is equal to 0, that means the resulting one must be equal to 0. Or this 0 also means, well, probably let me write this just into the as the same form. All right, so this is what we're saying is this 0 vector in f infinity is just a vector all the coordinates equal to 0, right? So then this tells us what? This tells us, well, all the x2, x3, x4, and so on are going to be 0, but we do not care about x sub 1. Because x sub 1 is 10, is negative 100, that makes no difference. As long as from x2, all the numbers equal to 0, so when you make that shift to the left-hand side, the x1 will be dropped. So then you still get a 0 vector. So then this tells us the null space of T will be x1, and then all other later coordinates all need to be equal to 0. And x1 can be, well, since we're talking about the f, so probably just putting f here. All right, so then this is where this t is defined, and this is where null t looks like. All right, so hopefully this give everyone some understanding on like what probably this right now is a subset we're talking about, right? What is this null t? Now, the proposition, first proposition here says if we're trying to prove is if t is in the L v to w, and then the conclusion is this new subset we defined is actually a subspace of V. All right, so this is a proposition. I see this is the proposition from the book. I think it's a definition is 312 in the book, and the proposition this is 314. Put a number here. 314 here. All right. Then we already did this, well, not exactly the same proposition, but we already did several proofs showing something is a subspace. That's one we definitely did that. All right. And then showing something is a subspace means you check 0 is there, you check this vector space is closed under addition, and the vector space is closed under scalar multiplication. If that the set is closed under these two operations, then that is a subspace. So we're going to follow the same approach here, right? So first, show 0 is in the null T. All right. So why 0 is in the null T? Because T of 0 is always equal to 0. And if I think we explained that before, but if you forgot of that, just remember the T of 0 is the T of 0 plus 0, because 0 plus 0 is 0. And then that is by the linearity of T, this is T0 plus T0, right? So if you add the additive inverse of this element, T of 0 is an element in W, so if you add the additive inverse, then you can get a 0 here. This 0 is in the W is equal to T of 0. Right, so then that tells you the 0. All right, we write 2 zeros here. I don't know if I should use a color or something to separate this, but keep in mind that the 0 in the pair of parentheses here is the 0 element in V, and then the 0 on the equation here is the 0 in the W, and when on this thing here, when I say 0 here, that is this same 0 in the pair of parentheses. This is in the this is in the null T here, okay. Of course, it's in the V, but it's also in the NOR T here, right? So that's the first thing we're trying to do. And secondly, we want to show that this subspace is closed under addition. That means show that if V1 and V2 both in NOR T, then the V1 plus V2 is also in NOR T. Right? And that is, again, follow the definition, right? Ask yourself, what is the meaning of the NOR1 is in V1 is in NOR T? That means there exists, or this is from your discrete math, there's an existential quantifier here, or there exists some kind of that means I was thinking the range there, but this means the T of V1 is equal to 0. All right, that's simple. All right, for the range, we need to find some pre-image in the V. But for NOR T, we don't. All right, so if we have V2 in NOR T, that means the T of V2 is equal to 0. So you add them together, you get a T of V1 plus T of V2 is still equal to 0. All right. However, since T is linear, all right, then T of V1 plus T of V2 is the same as the T of V1 plus V2. All right. Then from here, you can see what we imply is T of V1 plus V2 is equal to 0. So this tells us V1 plus V2 is belonging to the NOR T. All right. So this tells us this subspace is closed under addition. All right. Not very hard to do that, or as long as we have a clear understanding of what we need to do. All right. So the third thing, of course, we need to show if the A is in F, all right, and any V is in NOR T, then the A times V is also in NOR T. All right. So I will. Well, let me finish this. Then maybe for the range, I think everyone can do that as exercise, right? So this one. If the V is in NOR T, then of course T of V equal to 0. If we want to write just a few things quickly to explain this, we begin with the T or A times V, and here T is linear. Then because T is linear means that we have that addition property, and we also have that homogeneous property, right? So this is you have A of T of V, and well. Then this is A times 0 because V is in NOR T. All right, so that means, in other words, T of V is 0. So this is equal to 0. So this tells you that A times V is also in NOR T, right? So this tells us, now we know this NOR T is closed under scalar multiplication. All right, so altogether, by 1, 2, and 3, this is a subspace of the vector space V. All right, again, this is something belonging to the first vector space V there. All right, then this tells us the definition of the NOR space, and now we also comfortable after the proof. We're comfortable to say, well, there's a subspace, and what next? Well, next, let's make the connection between this definition and what we mean the T is injective. All right, and the injective is basically like the idea you have seen in your college algebra class, like one-to-one functions. All right, different inputs give you different outputs. Or the other equivalent way to say that is the same output implies the same input, right? So that is something. The concept everyone should already, at least at some point, studied that, or hopefully you still remember that. So let's go here to make this definition, maybe to the next page. Okay, here's our definition here saying a linear map, right, from V to W. This is called injective. Right. If whenever U and V, the two vectors from the vector space V, and the T of U equal to T of V, right? If you have two things, their output is the same, then we always know the U and v, they equal to each other. All right, so this is exactly the same concept as the one-to-one functions you have seen before. So what are going to be some examples? All right, so remember that one we talked before, like the t of xy or from R2 to R2 is equal to yx. Oops. Not sure why this moved. Okay. So that example is a good example to tell us that is one-to-one. All right. So yx. All right. So this is injective. All right. Because if you have a yx is equal to another one, maybe something like a qp, right? Then that means their pre-image xy and the PQ, they are the same. Right? That's pretty easy to clear. Pretty a simple thing to do this, to check this. And then what is not, right? So let's consider this one, like the txy is x plus 2y, 2x plus 4y. All right. So this one I'm saying is this is not injective, all right? Because the following reasons are, so generally speaking, the first example I did not write down the details, but generally speaking, when you argue the two things, when you argue a map is injective, this you need a proof, right? You need to assume the two outputs equal to each other, and then based on that, going back to argue the two inputs equal to each other. So you always need a general proof. And to show something is not injective, you only need one counterexample. You need a specific counterexample saying, well, here is one input, what it is. Here's another input, what exactly it is. And then the t applied on the first one and the t applied on the second one give you the same output. Then that's contrary to our definition, t is injective. All right. So here we're trying to make a specific counterexample here is because t of 2, -1, I can check 2 minus 1 is 0, 2 is 4 minus 4 is 0. So this is 0. And then, of course, you can put 4, -2. You can choose something else. All right. But this also gives you 0, 0, right? So then the different vectors in R2, they all go to the same vector in R2. All right. Then that tells you this is not injective. Let's add two other examples. Well, probably one more is enough. Let's consider this differentiation operator, right? So the input is a polynomial, you differentiate that, then you get another polynomial, which is a derivative. So this is also not injective, right? And then the reason to explain this, whatever the polynomial you use, right, it doesn't matter. You can say, well, I use a t of x squared, I get a 2x, and then I also can use the t of x squared plus another constant, maybe plus 10. I also got a 2x. Then this tells me this is not injective. All right, so that's, I think, all the explanation we're looking for. Give two different inputs, and then show their output is the same, so it's not injective. Okay. So next proposition makes the connection between the injection and the null space. If we have any linear map from V to W, then this T is injective if and only if null T is only containing 0. Okay, and it's not we already actually did that, right? So it's not hard to see 0 is always in null T, right? But what we're saying here is, well, if T is injective, then your null space is not going to be anything larger. So there's only one element there, and that one element is always there in this, no matter what the T you're talking about, right? As long as that's a linear map, the 0 is always there. So, but that's the only thing there. And then I think a more interesting thing to learn is the other way is, well, if you know the null T is just 0, then that implies the T itself is injective. In other words, two different input v1, v2, the t of v1, t of v2, they're always going to be different. All right, or if they're the same, then the v1 and v2 always the same. All right, so this only holds when you know t is linear. All right, we're going to see where the linearity is going to be used. Right, so we can prove either direction first, but we need two proofs because it's if and only if statement. Right, so you can assume one thing and then try to show the other, and then vice versa. For instance, if we assume the one direction is the t is injective, all right, then we want to show nor t is only equal to 0. All right, so why is that? Well, consider this: for any v which is belonging to nor t, or by the definition of the nor t, that means the t of v is equal to 0. Right? So if you think there is an element of v in belonging to this nor space, then that means t of v is equal to 0. But we also know the t of 0 is equal to 0. All right, that's always true, right? All right, so this is always true. Right? For any t, as long as a linear map from v to w, this is always true. So then this implies that t of v is equal to t of 0. All right? Because you have two things right now. Both go to the same output, right? So that's what we're saying. But remember, our assumption is we assume that t is injective, right? Well, since t is injective, then what this tells us, injective means, well, if you have tv1 equal to tv2, the v1 must be equal to v2, right? So if you have tv1, t of v equal to t of 0, then this tells you the v is equal to 0. And we do not have any specific requirement on v, right? The only thing we assume is this is an arbitrary element in the nor space. And any arbitrary element in the nor space, you always can follow this argument and show that it's equal to 0. So this tells us the nor t do not have any other things. It's just 0, right? And this I think this direction is pretty easy to think about, right? Because the 0 itself goes to 0, right? So here's a 0 in the v, and it goes to 0 in the w. We know that's always true, right? And then if you have another non-zero vector in v also go to 0, well, then you actually contradict the fact that t is injective, because you have the 0 here and a different number here, a different vector here. They both go to the same thing on the other side, so that's not injective, right? So injective will guarantee you there's only one thing which is going to work, and we know there's one, it's 0. All right, so that is the proof of the one direction. Now let's do the other direction. We're going to assume, I think this other direction is more interesting, is assume the nor t only has 0, and we want to show the t is injective. So what do you mean the t is injective? In other words, all right, so we want to show if nor t equal to 0 and t is injective means if you assume that t of u is equal to t of v, then the u and the v, they always equal to each other. All right, no other possibilities. All right, so that means the t is injective. So right now so our two things you can use in your proof, two assumptions you can use is nor t is only containing the 0 vector in v, and then secondly, we assume that to begin with, we assume the t of u equal to t of v, right? So, but this not immediately allow us to, this equation t of u equal to t of v, we have to do something, allow us to use the linearity of t, and allow us also to use the assumption that nor t is equal to 0, right? Because right now, you don't see anything to do with the nor t. But remember, the nor t means that t of 0 is equal to 0. So you kind of have to create a 0 somewhere. And that way we think about this is, well, t of u equal to t of v, that is equivalent to t of u minus T of V is equal to 0. All right, no matter what the T is, you just add the additive inverse, right, to both of the T of V to both sides of the equation, so you get T of U is minus T of V is equal to 0. So we're good with that. And then what next? Well, so that's where you need to use the assumption that T is linear. All right. All right, so now T, actually let me make it clear. Right? So where this T is belonging to LVW, and we have this, right? So this is where we use a T belonging to the LVW because it means T is linear. Then that means you can combine this into the T of V minus U minus V equal to 0. All right, so that way you have T of something equal to 0, and we want to say something about this input. And what can we say about this input U minus V? Well, since the null T is 0, that's the only thing going to actually to be mapped to 0, or is 0. And then that tells us the U minus V, right? Actually, even before this, that means make it even better, saying, well, this means the U minus V is in null T. How about that? So this is by the definition of null T, right? So that means you have T of something equal to 0, that's in the null space. And then also, we know the null T is only containing this 0 element. So then this implies the U minus V equal to 0. And then this implies the U is equal to V, and then this implies the T is injective, right? By the definition of injective. Okay, so then therefore we proved this is an if and only if statement. In other words, all right, so now we have two different ways to verify a given linear map is injective or not. One is to follow the definition, set the TU equal to TV, and show the U equal to V. That's one thing to do. The other thing is you can actually check the null space, say, well, what actually included in the null space? If the only vector in the null space is a 0 vector, that can also you can also conclude that linear map is injective. All right, so that's the proposition. Let me see the book here. Right, so this is the one proposition we proved in this book. This is the proposition 316. All right, let me write the number back. So I think this way, we probably a good place to stop for this recording here. All right, so we defined what is the null space, and then we introduce the injective, and then we prove this proposition. So in the next video, we'll probably go a little bit quicker, skip some proofs, all right, but we're going to define the range. We're going to say, well, the range is a subspace of W, not VW, all right, and then I'm probably going to skip that proof, and then we're going to also define what is the surjective and make connection with the range. All right, and so then in the third recording, we probably can prove some main theorem in this section and the corollary. All right, so see you in the next video.